This is a survey we did last year of people that, mostly people that I know, professional folks, not CSUCI folks per se, although some CSUCI students participated. And the question was, what programs do you use for statistics and graphing? Now this is before Plotly wasn't really a player yet, so you'll notice that there's no Plotly here. But this serves to make the point. So let's have a look at this. Can everybody see these graphs? Is that okay? Ben, can you guys see those in the back? Yeah, all right, good. So here on the bottom panel, these are CSUCI students. Let's see if we can make it a little bit darker here. CSUCI students. This graph are professional folks. And the topmost graph, just a little teeny bit cut off, is everybody all combined. And there's a couple different colors here. And then, so this is a percent of all the respondents that responded to this online poll. And then in this case, these are these different programs. I'll run through them in a second, but just to orient you, the leftmost maroon color is people self-identified using this particular program for statistical analysis. The next one over, the purple, is they use for exploratory graphing, maybe not their final thing they're going to put in the paper, but just the quick and dirty, hey, what is this? Is this thing related to that? And then the lightish pink color over here is something that they actually use to produce formal graphics that they would submit to a journal, say, or use in a formal public presentation, something of that nature. So reading off from left to right, we have Excel, ArcGIS, R, SPSS, SysStat, a program called SigmaPlot. This is, everybody writes this, the program is JMP, but everybody pronounces this as JUMP. MATLAB, Adobe Illustrator, Google, just the whole suite of Google, online Google tools, Google Charts, SAS, Numbers, which is part of the Mac OS Office, and Estimate S, which is a plugin for Excel, I think. So there we go. So stare at this for a second and tell me what you guys think. Again, it's a little bit cut off here. Everybody on top, and then I think the most interesting is the professionals compared to you guys. So stare at that for a second and tell me what you guys see. Hold. Okay. So Excel is has on average the most things, or mostly dominant. Not necessarily every single category, but at least most of the categories. Yes. And what else? Somebody, Kara.
It's definitely like more even between the programs for the professionals. So maybe they kind of know what they're doing and what works in their own niche, while students really want to do Excel or ArcGIS because
okay.
they learn in school.
What's the top one again?
The top one is everybody combined. The top one is all of everybody. Just doesn't matter, just as long as someone responded to the poll added together. So right, so a couple things here that we see. Some things dominate. The things generally speaking, on the leftmost side of the x-axis are most widely used by people. I should say, people could have ticked more. It wasn't you had to pick which one you used, right? They could have selected multiple things. So if we were to add up all these bars on, let's say, the used for statistics, it would sum to more than 100%, right? That's the first thing. Second thing is as Kira was saying, that the professionals is a much more even, smooth distribution, right? Going from the most popular, the next most popular, next most popular, whereas with you guys, you don't have anywhere near, on average, the diversity of programs that you're using, right? And that makes sense. That makes sense because you guys are young. That makes sense because we do all kinds of stuff, and we don't have 1,000 million programs in here for you guys to pick from. The reason why I think this is interesting, and this is basically my my network of people, or at least sent out through my network of people. So these are folks that are doing basically the kind of jobs that many of you are interested in getting. So this is to Park Service people, and this is to consulting companies, and this is to government agencies, all that kind of stuff. So this is basically ESRM fields that this is directed at. So so interesting. Even in the profession, in the folks that actually have jobs, Excel dominates, which is interesting. I was a bit surprised by that, to be completely honest. And then it's much more even. Then if we come down here, it's much more evenly distributed. ArcGIS, R is huge. Look at that. R is number 3. I mean, roughly speaking, is either number 3 or number 2, but it's in the top couple here. Whereas almost none of you guys use R. R is free. R is open source. R will always be free. R is rapidly becoming probably the most widely used stats and graphing platform out there. So we'll talk about what it is. But R is command line driven. R is not pull down a menu and click this box. It is type this thing and this thing and this thing, and then return, then type this thing and this thing, return, then type this thing. So it's not as easy for those of you that aren't familiar with computer programming. Those of you that have taken intermediate GIS and have taken a little bit of Python or learned a little bit of Python, be pretty straightforward. But it's created by techie people and not too worried about making it available to the masses, right? So there is a relatively high bar to enter that using R, but once you're in there, it opens up a tremendous amount of neat stuff. Next is SPSS. So we have SPSS licenses here on campus, so that makes sense. Then boom, next we jump up really high, and so we tend to have a higher penetration of SPSS than the average professionals. That's because SPSS is primarily designed is primarily used in the social sciences. And so we have it because we have a gigantic psychology department and a big sociology department. And they think SPSS is awesome. And so when it comes to figuring out what licenses we're going to get, right? ESRM, we're a relatively small program. For just historical reasons, when we were trying to figure it out back in the day, someone said, hey, SPSS. And so we've stuck with it. It's not a horrible program by any means. It's a useful tool. But it's maybe not all the things that we might like to have, but notice we have it. And then as we go to the right, very few of you guys have used any of these programs. They range from GUI interface, easy to pull down, kind of more intuitive type things, to online tools such as Google, to more command line driven, more techie type things such as MATLAB. Okay, so that's the first thing. Interesting. So in other words, your familiarity isn't necessarily the familiarity. If you go to work for a consulting firm, they might expect you to know something about some other programs or some other environment. Okay, this guy gonna fit? Yeah, okay, this guy will fit. All right, next. What are the most common graphs? Here, look, don't even look at that. Let me stop this right here. Okay, how about this? So when you guys are working on your first graph, your key graph, the thing that's going to be your key test of your central hypothesis, what gross type of graphs are you guys making? Let's do a little count here. We got Scatterplots. We can put that up here. We could put up a bar. Somebody said bar charts or bar graphs. Line plots. Pi. Got to vote for pi. Okay, histogram. Histogram. Sure, histogram is a special kind of bar, I'd say, but okay, cool. Any other quick ones? Okay, that's fine. Okay, so for those of you that are doing your key, so we're all working on thinking about producing our first graph, right? We took a little stab at this last semester, but now we're getting more serious about this. So your central graph, who amongst you is going to have a central graph that's a scatter plot? Raise your hand if you think that's you. 1, 2, it's okay. Hi, don't give me this wimpy thing. 1, 2, 3, 4. Okay, so 4. How about bar charts? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 16, 17. Okay, 17. And how about line? 1, 2, 3, 4. Wait, the hands keep changing. Ready? Line. Okay, I'm going to close my eyes. 1, 2, 3. Line. Hands up high. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, pie charts. Oh, Ben's going to try to represent pie. Don't give it to me, dude. You already gave me one. That's totally, I'm going to put pie. Dominic voices pie, and then he wimps out. I understand. I like pie. No, I don't. Okay, so right, I would say that's pretty typical. So, and there's nothing wrong with that. I would say scatter, bar, and line, for most of what we deal with on a typical daily basis, I would say that's about 75%, 80% of the kind of graphs that we generate typically. So that's all good. Let's have a look over here, though. Let's have a look at what the wider community uses. Okay, here we go. So let me orient you to this one. Now I'm changing it up on you a little bit. So here on the left axis is the type of visualization that we're talking about. The salmon color, the uppermost, is you guys, CSUCI. The professionals, folks that have jobs, is in the mustard color. And then the blue is just overall everybody mushed up together. So here we go. So Scatterplot is, and so then this is sorted by the all respondents overall. So Scatterplots, and again, this is the same thing. So the question was, the question was, what graphs do you use on a regular basis in your job or your employment? And so here we go. Scatterplot, just about, almost 90% of everybody uses these scatter plots. Even you guys, at least 80% of you guys use scatter plots. So there we go. Really close on the heels of Scatterplot is bar chart. And look at that. Not surprisingly, look at that. You guys voted more bar charts here. And so our population this spring is very similar to our population last spring. We do this in that, yes, a lot of you guys are interested in scatterplots, but bar charts seem to win out. Line, again, overall, grossly similar. And then once we start going here, histogram, which we could consider a type of bar chart, is next. And then we decay down as we go farther forward. Anything stick out to you guys about this? About the type of graphs that Ben? Okay, so again, just like the last graph, you guys are in there. You guys are making all the types of graphs that people in your field are generating. But again, you're not as evenly distributed. You guys tend to really clump. You guys tend to use a few and don't necessarily have as diverse a palette of graphing, Gesundheit, as other people have. Anything else? Anything else? Gesundheit. Jump out at you guys? It's very exciting, I know. Box plots. What? Andrew likes box plots. Oh, you mean the fact that we don't use box plots very much. That our salmon color really, histogram is solid and map-based graphing is pretty solid, but there's this dearth, especially compared to our, it looks like for box plots, that's roughly 16-ish% versus 40. So that's about something like 15, 20, 25-ish percent difference. That's a pretty large difference. Okay. Anything else? Look, Dominic will be stoked because pie charts are up there. That's cool. That's good. Okay, so basically the same story, right? That generally you guys are, and this makes sense. It doesn't mean you're bad or horrible or stupid or something like that. It just means you guys are young. You guys are starting out. You guys are learning, right? We have to walk before we run. And so it makes sense that you guys are focusing on some of the more basic or foundational types of data representations than someone who has many more years of experience than you guys. Cool. All right, what else can we play with in this? Here we go. So this is the type of statistics that these guys or these people are doing. So here we go. Same thing. This is the same color pattern as last time. CSUCI up top. The goldenrod or yellow color are the folks with the full-time job, and then everybody together is with the blue, and it's sorted by the all respondents. Anything up there unusual to you? Anything up there seems strange to you guys? So again, the same patterns we saw before with the professionals is a relatively even, a much more even distribution of the use of these tools, whereas you guys tend to be much more clumpy, right? Relying on fewer types of statistics. So the ones you guys are most familiar with are descriptive stuff. Next is something like analysis of variance, so comparing categories, comparing means. And then what's next for you guys? For you guys, next is chi-square, it looks like. And then what? Then maybe bootstrapping or mark recapture, and then we kind of and then we sort of decay to a small percentage of folks doing the other ones. Okay, so again, it doesn't say what you're doing is wrong. It just says maybe there's other things you can think about. So let's start with a scatter plot. Let's start with a analysis of variance or something like that. But realize if you want to go deeper into your data, it's possible. And in some cases, your data is hard to figure out or we're not sure what to do. In some cases, it's just you don't have the full set of tools. So that's where you can come talk to me, talk to Dr. Steele, talk to whomever, and say, hey, is there a way we can think about looking at this data set in a new way once we have the basic foundational stuff under our belts? Okay, questions about that? Anything in here confusing, or Julie?
I'm kind of surprised that students don't take error estimation into account.
Yeah, I'm not. So right. So error estimation is not necessarily, yeah. Well, it's a tricky thing. So it's trying to figure out where the sources of error might come from, and it's something that's worth doing, but it's not necessarily a pull down click menu. And so when you guys are new at this and getting started, it's not surprising to me. Anything else? Any other observations you guys have about this? No. Okay. So here is, I think, another interesting one. This one's a little bit small. Can you guys see it in the back? Is it okay? All right. So this is not what of those groups that you're saying. It's rather how diverse is your statistical palette, right? And so here we go. So this is the percentage of again, salmon are you guys, the goldenrod are professionals, and the blue is everybody all together. And so let's look at this. So here we go. So going from people that reported or that ticked in the survey only a single statistical method that they used, going on up to a few people ticked a gazillion of them, 15. None of you guys clicked 15, or none of our former colleagues. So the most any CSUCI student ticked was 6 different types of statistical tests they've used or routinely use. So again, this just says that you guys are young and that you're familiar with a couple of these things, whatever they be. And on average, you guys use a bit more than 2, whereas the average professional uses on average a bit more than 6. different types of statistical tests commonly. So again, as you guys are going to get deepen into your field and become familiar with the specific needs and data requirements of your subdiscipline, you will pick up these things as we mature, as we go on. Anything else about that? Anything else interesting? Okay, cool. Is that all I had to say? Okay, oh, then lastly, this is just the graph. Same thing for the graphs, the types of graphs. So this is much more even, right? So when we talk about graphing, it's easier for us to try out different types of graphing categories than it is to try out different categories of statistics. And that makes sense. So, but nevertheless, you guys are still young, and so you're using a bit under 4 on average types of graphing display strategies, whereas professionals are using a bit more than 5. So you guys are, that's a much more even parity there. Cool, makes sense? All right, so here we go. The basic idea here is we want to know, does thing A differ from thing B? So here's some, on the x-axis here, here's some measure of things we're counting. Okay, this could be whatever you want to pick. This could be how tall people are. This could be the categories of whatever the heck. And then on the left here, on the y-axis, this could be the number, the count, right? So we would, if we count a couple of things, we would drop a couple of I don't know, dots. Oh, geez, dots like that, right? So we got a couple of these things, and we would keep going up, and we'd add these things up, and we would eventually build up a distribution. And for many of you guys, okay, let's clear these guys out of here. For many of you guys, the types of populations that you're working with will follow something like a normal distribution. Something like that, right? Something funky and weird. Something vaguely like that. Okay? So there we go. There's 2 key variables that everybody is going to want to be able to articulate from each of their populations. Now, using the term population not in the biological sense, it could mean that, but in the statistical sense. So population, the thing we're sampling. So the first is, where the heck is this stuff mostly found? What's the most common level of this thing? So we call this guy the measure of central tendency. And then there's going to the number next is how spread out is that thing? How wide is it? So we could envision another population right here. Something like that. And I could make it a different color, but I won't. So the question is, hey, does A differ from B? That's the central hypothesis you guys are generating. Do I have a different number of plants on Santa Rosa in this creek versus that creek? Is the temperature higher in this creek or that creek? Do I have more coyotes in this camera trap or that camera trap? However you guys slice it, whatever your particular question is, this is the nut for almost everyone that we're trying to crack. And so, again, the key things we're going to want to have here are central tendency, which is going to be this thing right about there. And then we're going to want to have some measure of the spread of this thing. Oops, that was kind of weird. Look at that. That was zany. So measure the spread. And the spread It's going to be a measure of dispersion. That's sort of highfalutin statistics talk. What you can use for the term central tendency is average or mean. You could use, there's a bunch of things, mode, there's all kinds of, but we'll just use mean or average. Okay? For the spread, how wide-ranging are the values that you're measuring, the population that you're measuring. That is going to have maybe some other words you've heard, variance, standard error, 95% confidence interval. These things are all related. And really it just gets down to your particular question, the flavor, and how we compare them. So what we're ultimately trying to do is we're going to take, and for most of you guys and most of your hypotheses, we're trying to say, hey, does the tall lump statistically significantly differ from the small lump? And recall that statistically significantly differ from the small lump is a big fancy way of saying we think it's really, 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 really unlikely that this would happen totally due to chance. It's not saying it couldn't happen due to chance. We just think it's really, 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 really unlikely. And it's too hard to say really, 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 especially when people used to write stuff out by hand. So we invented this term statistical significance. So that's what we're moving towards. So when you guys are first conceptualizing what key graph, what key piece, I mean, you guys know what data you're collecting, but when it comes to how we're going to communicate that information, it's going to get down to how do I communicate if these things are different or if these things are the same? And so I suggest, as we did this a little teeny bit last semester, but just sort of barely scratched the surface, the best thing, take a piece of paper and a pencil and sketch it out. Sketch out what you think would be a killer demonstration or test of your hypothesis, a killer articulation of all this data you've collected. Start simple, and then once we start mastering that, we can start maybe adding on some complexities, some depth, some additional data on top of other data. But for now, let's just keep it simple and straightforward. Does this make sense? Yeah? Okay. We have several tools at our disposal to do this. Plotly, I think, is a great one. You can, of course, use Excel and other things. There's two basic types of... Okay, so the first step is going to be, let's get our data organized. Let's get our data in a useful shape. And as we said last time, last semester, it's a non-trivial thing to get our data into the shape that we want them, that we need them to be in to do a particular statistical test or to do a particular graphical display. And so it's going to take some tweaking and some trials, and we got to have this thing arranged this way and invert that column and right? Every program that you will use will have some weird quirks. For example, when I type dates into Excel, I put month, day, year, and then time. That's not how Plotly interprets stuff. Plotly needs it to be year, then month, then day, for example. Not a huge deal, but there's a little tweaking in every computer program. And so sitting here trying to make our first graph, even if we don't have all your data yet, is a great exercise and will help us get things organized. Some programs are really powerful and will allow you to do both high-end statistics and high-end graphing at the same time. Plotly is getting quite sophisticated at some of the graphing stuff it can do. It's not really yet up into the high-powered statistics. It's doing more stuff all the time. But I would say Plotly is an example of something we really want to tweak and get our data nice and really tight the way we need it, and then bring it into Plotly. Right? So a couple iterations might be helpful. Plotly now have plugins, so you can graph directly. You can have an add-in in your Excel here. Okay, so mine, I've added this in, and so if you look on my Excel spreadsheet, right up here on the right, you see this thing that says Plotly. It's a part of Excel now. So if I want a graph, I can generate a graph, and then it'll automatically barf it out to, it's probably a more technical term, but we'll liberate it to the World Wide Web. And then we can access it, share it with our colleagues, our partner. We could do collaborative graphing. You could send me the version. I could give you all that kind of stuff. But here's some data, let's just say, classic case. We want to compare, let's say, the length of these. So we have two populations of fish in pond A, fish in pond B. Maybe they're birds in field A, maybe they're birds in field B. Maybe their amount of sediment that came down in draw A, sediment in draw B. So the question is, how can we get some rough idea what's going on here? I tend to poo-poo Excel in terms of its statistical things because over so many years they've gotten things wrong. And the underlying models have been incorrect. I'm sure they've probably fixed almost all, if not all of those by now, but it's left me very wary of Excel for anything sophisticated. For basic stuff, for basic manipulation, Excel's great. It was invented by accountants doing, keeping the books for companies and for people's taxes. So for that kind of stuff, it's just great. It's awesome. So everybody should at least be able to do some simple calculations in Excel. So I want to make sure you guys know how to do those right now. Okay, so if you guys have your computer on, that's great. If you don't, maybe you can fire up your computer. And if you guys could just fire up Excel, just so you guys could all try this. I'll give you guys a second. Okay. So then everybody look up here. Actually, first, everybody just make some random numbers in column A. Just type in a couple random numbers, 5 or 6 random numbers. Then in B, same thing, type in 7 or 8 random numbers, whatever, just so we have some stuff to play with. So we have numbers in column A, numbers in column B. All right. All right, cool. Everybody's going to look up here. So what are the two, at a minimum, what are the two key pieces of information we need to describe a population's distribution?
What's the most common?
Right, what's the most common measure of central tendency, right? And a measure of the spread or dispersion, right? So so I'm just going to tell you right now, as just write this down. Just write this down. To start with, if you guys don't know where to start, mean. You want to calculate your mean. And for most of the projects you guys are doing, you're going to want to calculate a standard error or 95% confidence interval. So just start there. If you guys aren't familiar with this stuff, you don't remember it from statistics class and all this and that, just start with those things. Write those down. And that'll get you 90% of the way going. Okay? So here we go. Let's talk about that. So let's make sure everybody can do some basic statistics or calculate some basic statistics inside Excel. Okay, so the first, yep. So mean is the measure of central tendency most of you guys are going to want to use. And then for your measure of dispersion, I'm going to suggest you guys either standard error or 95% confidence interval. There are many more options, and in some cases they might be better, but just start with that and that'll take care of most of you guys, I think. Okay, so let's have a look at this, and let's just remember how formulas work in Excel. If I just go over here in this cell, so everybody's looking up here, right? Everybody's looking up here. My eyes are up here. So if we look at this, if I type something like a number, 88, or letters, AS, okay, there we go, they're there. And if I move the cursor over here, if we look at this section inside Excel, we see that the exact things that we typed in that cell are there. So the computer program has saved for us in cell, what is that, A24, the number 8 and the number 8. the other thing that Excel can do, let's delete those now, is we can enter stuff as a formula. And the way we signal a formula is we type the equal sign. Then it says, hey, this is something funky, right? So I'm just going to start with typing equal sign, A-V-E-R-A-G-E, parentheses. And I could do this. I could click this cell and then hit the comma, and then click this cell and hit the comma, and click this cell and go on and on and on. Okay, that's totally legal, no problem. But we don't have the time for that. We want to be slicker. So I'm going to click and hold here and scroll up. Just like that. Then I'm going to close parenthesis and hit return. So check it out. Now, this just told me the average of my population 1 is a little bit more than 49. Realize that there's no 49 typed anywhere, even though it looks that way to you. And we can tell that by putting the cursor over the field, over the cell. Oops, what did I do? Boom, over the cell, and check it out. Right here, if really we had typed 49.476, blah, 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 it would say that. It doesn't say that. So the only thing the computer program is saving is this mathematical operation. And then the processor, as it's attempting to display it for your human eyeballs, is running through the motions and generating that number. Okay? So there we go. We could put, here, we could do something like this. Insert a column, and I could just put a note here. This is my mean, okay? And let's calculate standard deviation. Let's put a note here. So same kind of idea. I hit the equal sign to tell it, hey, we're going to go into calculation mode. And then I'm going to say the fancy words for standard deviation in Excel speak are STDEV. Open the parentheses. Same thing. Click, hold, and drag. Or I could click and then scroll up to the next one. Hold the shift down while I click. Close parentheses. Boom. Right there. So now what it's saying is for this population, the fish, if it's fish length we're talking about, the fish length is 49, I don't know, let's call it 49 centimeters, 49.47 centimeters plus or minus 19.9 in terms of the standard deviation. Cool? Everybody with me on that? The reason it's worth putting some time into this is because you can get your data set up in a nice way, and then as you get next week's data, next week's data, next week's data, if you plug it into the same pattern, you can get the answer right out, get the answer right out. So check it out. Right now, if I come up here and I copy these dudes and I put them to the right and I hit paste, what I've actually done is I've actually copied the formula and turned it and put it over. And if we have a look right here, this says the average of B2 to B22. If I go to the right, it's the average C. So it's relative, right? It's kept all the arguments and all the operations. It's just chunked it over one column. All right, cool. So the last little bit, let's do standard error. Does anybody remember for most of the stuff that you guys are doing, the way we calculate standard error? Formula for standard error is going to be standard deviation divided by, ready? Here comes some math. Everybody close your eyes. It's going to be okay. It's going to be okay. Oh, yeah, Kira's totally asleep already. Okay, divided by the square root of the number of samples minus 1. It's not that crazy. Standard deviation is a fine measure of dispersion, but it has some issues. One of the problems with standard deviation is it's very sensitive to, it scales with the mean, which means the variation looks very small if our average was 3. Versus if our average was 1,000, it would look quite large. And so that causes some issues. Standard error, if we note here, look in the denominator, the sample size is on the bottom, so it's standardized by the amount, by the size of our sample. So it's less sensitive to that type of problem. So that's why we like to use it. There's another reason we'll talk about in a second. But how do we calculate that? Let's check it out. We come up right here. We could do it all in one line, but since we already have standard deviation above me, why don't we use that? So as we said from our formula, standard error equals standard deviation divided by, I use the slash for divided by. I'm going to open my parentheses. Now, let's count this up. 22, so this is 21. So we could just say equals 21 minus 1, right? We have to make a square root of that. So we use the code for square root in Excel speak is SQRT, open parentheses, and then over here, close parentheses. Standard deviation divided by the square root of the sample size minus 1. That's all that says. We use parentheses because this is a stupid program. This program doesn't understand what's going on. So it follows all of these rules. And the rules are, we do what's inside the parentheses first. The most internal part of the parentheses first. And then we do what's outside of that next, and that next, and that next, and that next. Otherwise, if we didn't use any parentheses, it would come out with different, it would do the square root of 21, and then it would minus 1 from that, and it would get all crazy. So we use the parentheses to make sure it's doing things in the order we want it to do. So now this might be a little bit of a problem, because check it out. Right here in population, in our first population, we had 21 fish that we counted. But in this next population, we only had 14. So we could do this. This would totally work, but we'd have to go in every single time and count. And if you were measuring 50 things every time, you'd be golden. But in the real world, we dropped our bucket. We stepped on the barnacle. We screwed up something, right? So we don't always have exact, even though it would be nice, we don't always have exactly the same sample size, for every population we're checking out. So if that's the case, which is going to be the case for most of you guys, what we can do is we can do the same thing, but we're going to say, hey, you Excel program, you count how many fish there were there. I can't be bothered because I'm much too important, right? I'm a professor, right? And so we're going to do that by using another command from Excel called count. And count, I'm going to put in the place here. So instead of saying 21, I'm going to have Excel figure out the number of things that were measured, and then it'll throw the number in. So I do it like this. Okay, this is what I want to show you. So first, the thing that's nice about Excel is if I click in here, check it out. Let's look, and now everybody look up here. So we see we have this B25 thing that looks blue. Then I have one colored parentheses. Then I have some other ones that are purple and maroon. And so everything is, so the parentheses are matched up so we can see which one we're talking about. But then the values are different colors. And so if we come up here, actually what's going on is this, so here we go. So the blue, so to help us visually with this, hey, B25, here's this thing. And what's that thing? Oh, blue, oh, here's what, I clicked on this one. And then the range of the count is this green guy. Boom. So now we can move this guy over, and it's going to give us the correct formula no matter what. So when we talk about getting our data in the right shape, if this is something that's relevant to you, you're going to want to get your data that way, then all you got to do is drop, so the first time or two, it's going to take you a little bit of time. And this is just one example. There's different ways we can format our data. So you're going to want to get it formatted in the right way so that when you start, keep going the next month or two as you're pulling in data, you can just drop, copy, paste, boom, drop, copy, paste, boom. And you can be looking at it, grossly before you even graph anything. Hey, is my number going? Are the fish getting bigger? Are they getting smaller? Are they roughly the same size? So the first step, before we even talk about what statistics we're going to use, let's get the qualitative story. Did your fish get bigger? Did your fish die? And you guys should all understand that level of your data. Was there more soil? Was there less soil? Cool? Okay, so to reiterate, the two most common formulas I would suggest you guys use for most of your stuff are going to be average, or the mean. And in the context of Excel, if you want to calculate that within Excel, you can just, boom, throw it in right there. And type equals AVERAGE, parentheses, and then the range over which you want it to work, close parentheses. Standard error is the standard deviation, which is just STDEV, right, over the range of which we're talking about, divided by the square root of n, which is this guy, n minus 1. And we're good to go. Let's talk real quickly. Let's look over here at the whiteboard real quickly. Let's talk about the three most common types of graphs that you guys will be using. Scatterplot, which is, right, x and y in a bunch of boom, 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 boom. Okay? We have a line graph. And we have a bar chart. Now, in theory, you can use any of these whenever you want. But by good graphical design, you shouldn't use those anytime you want. They imply slightly different things about them. Okay, so let's start with our line. Okay, so let's start with this guy. So here we go. Here's our line graph. Something like that, maybe. Okay. When might you guys want to use a line graph, a line chart? Colton.
For like our sand movement, beach profile. Beach profiles.
Okay. Beach profile. When else? Say again? Ooh, I would say probably not student test scores, and it will become clear why in a second.
Changes in population size.
Well, here maybe, yeah, over time maybe. So the key part of a line graph. Now we could have measured, let's say, the temperature. Maybe this is temperature over the course of the hours of the day, maybe. And maybe we had a little sensor and it was taking a reading every second. Beep, 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 beep. And maybe this is a bunch of little teeny tiny dots that we just can't see. And then we joined them together. Or maybe it's like 1, 2, 3, and then nothing over here. There's 4 and 5 and 6. And we join those together with some type of curve fit. In any case, when you show a line, what you're doing is you're implying relatedness from the point just to the left to the point just to the right. So for example, this point right here, what we're saying is, doesn't matter. Okay, what I'm saying is this point here came after this point. This point here came after this point. So the idea is that this point in the center bears some relationship to these two. It's on a continuum. So maybe it is like Colton was saying. Maybe this is distance down the beach. And so this little area, maybe we started rising. So it's going to rise, 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 rise. So these guys are related to each other. Okay? Does that make sense? Everybody with me? So time, distance over some like real spatial scale, right? The idea here is that this is a continuous variable on the x-axis. Okay, here's a scatter plot. When might we want to use a scatter plot?
Population variances.
Population variances, maybe. Okay, what else? Yes, most typically is when what Andrew's saying is when we're trying to explore the dependency, the specific dependency. In theory, all of these graphs are exploring the dependency of y on x. But if we're really explicitly trying to look at that, scatterplot's a great way to start. So let's say x is what amount of drug you gave the mouse, and then on the y-axis it was how hyperactive the mouse got after receiving the drug. Okay, so each of these points, so the implication here now, hey, are these points connected with a line? No. So the implication here is each of these points are independent from one another, unlike the line graph. The line chart, we took a measure and then walked 1 foot and took a measure, and then walked 1 foot and took a measure, or took a measure and came back the next day and took a measure and came back the next day, right? In this case, it's all over the place. Shotgun. Okay, so scatterplot is when these data aren't each datum isn't necessarily related to one another. And we're exploring that. Is that cool? The third broad category, there we go. Here's a bar chart, here's a bar graph. When might we use a bar chart? Say again? Counting something, maybe, okay. What about the relationships of the relationship of variables, say, on the x-axis? Right. There's no relationship, or maybe it's not evenly spaced. So it could be eye color. It could be the behavioral response that you saw. I just used a bar chart a little bit ago. What was I showing? Right. The different types of graphs, for example, right? A pie chart, let's say if number 2 is a pie chart, it's not inherently less valuable or on a lower extreme than a scatter plot, right? So therefore the bar charts, the bars here, they're separated, and sometimes with our eyeballs we look at that and it implies that they're evenly separated, but it's not true, right? They're categorical. So when we have categorical data, a bar chart is a great thing to utilize. Now, is it always 100% that way? No, these are fluid types of displays, and you can force these things to do whatever you want, right? Because you guys have power, you have control. But an educated viewer will look at a bar graph and see categorical things, or at least not evenly spaced variables. Scatterplot is an attempt to explore the relationship between these two things, collected independently, hopefully. Line graph is something that's going to be on this continuous spectrum that we were sampling along. Does that make sense? Okay, so out of curiosity, now, and I don't care one way or the other, but I'm just curious. So you guys said your prediction for scatter, or what you were thinking of doing for your first graph, scatterplot, bar, or line graph, you guys are looking at your populations. You're figuring out, how am I going to calculate my central tendency? How am I going to calculate my spread, my variance? And while you're absolutely free to use whatever graphical display you'd like, the 3 most common for most of your stuff, at least at this initial stage, are going to be line, scatter, and bar. When you generate these things, for example, when we generate our bar chart, you're going to want to put, you want to tell me what this is. So if our bar chart here, if each bar is the mean, we're going to need to throw on our measure of variance, right? When we actually put it, so we're going to have error bars on that. In some programs you'll use, they'll calculate that for you internally within the program. In others, they might not. But you guys now know pretty much everything you need to do to make that yourself. So let's check it out. So let's jump back really quickly, and then we'll take a break here. Let's jump back really quickly to our Excel. And nobody type, just look here. Check it out. Here's my population 1, or maybe it's my population at time 1, let's say. So here we go. Here's my mean. Here's my standard error. If I wanted to create my if I want to create my three curves, here's my mean. Then I'm just going to say equals mean plus standard error. And here I'm going to say equals my mean minus standard error. Boom. Right? Now if I go through, I would have all the points that would comprise my mean, the central part of my line. And then my variance, my standard error at the top would be comprised of these guys. And then similarly, the bottoms would be this. So I would have essentially 3 lines I could just plot up and boom, right there. No problem, doesn't matter what program I have. You guys can calculate your own estimate of the central tendency, graph it up there in bar chart or in line graph form, whatever. And you can have the measure of the spread. And then it starts getting fun. Then you can start to look at your data and go, oh, what is this starting to mean? And then we can start talking about how we can explore this farther. What statistical tests might we want to apply to this? What this and that. So that, everybody cool? It makes sense? So it's not super complex. It's just, and what it really gets down to is probably you guys are going to have to go through some iterations, and that's totally cool, right? You're going to try this, you're going to screw it up. Ah, damn, right? That's fine. Let's tweak it out. Oh, I should have had the data aligned like this. Okay, let's tweak the data, let's get it right. So even if you guys don't have most of us are still collecting our data, totally cool. Let's put in some fake data. Let's guess as to what we think it's going to be. And you can go ahead and start tweaking that graph. Real quickly before we take our break, I just want to point out a couple components of good graphing. Labels. So our x-axis here, I'd want to label this. I don't know, what is this? This is blah, blah. Okay? And then over here, this is going to be blah. This is going to be okay? Generally, though, I don't just want to say I want to put the units of okay? So I'm going to say the variable, and then I'm going to come up here and put it in parentheses, usually. I mean, we could talk about ways to do this, but generally parentheses, and then say milligrams or something, right? So it's going to be the value represented, the variable, what's the variable that we're displaying here. Then what are the units of that variable? Then we're going to want to have a title. Okay? So our title is not going to want to be blah blah versus right? It's going to be something descriptive. So in this case, it looks like as we go to the right in this, if this is a quantitative thing, as we go to the right, there's more blah blah, or there's more over here to the right than there is to the left. And so we would say the title might be something like maximum at level 6 or something, right? So we generally don't want to say graph of my results, right? We want to, again, the goal is to lead our audience along with us. Pull them along with this. You guys want to be the ones in control. Look, here's this awesome project I did. See? It shows this. And then finally, okay, one of the most common mistakes you guys make is somebody you guys will do this. You guys love to do this right here. Mean that's not right. Because this is not mean this level right here is the mean. But we're showing both the mean probably and the variance around this. So we want to get rid of that mean. Don't put the mean in the label here. Instead, let's insert some text somewhere and say something like bars equals mean plus or minus 1 standard error. Right? So now I haven't put the title in here, but we have a title. We have the labels, the axes labeled. We have the units. And we have something here so that anybody, if they flip into the middle of your thesis, if they walk up to your poster up in Sage, they'll walk up and they'll check it out and they go, oh, I see. This tells me wonk-a-wonk wonk. And I can, what are the bars? Oh, I can see it right there. So it's all transparent. We're not hiding anything from anyone, right? So it's all straightforward. No fancy, you don't have to read 17 pages to figure out what it means. It's all right there.